So we have a point charge, a positive point charge, and we know how the electric field is from a point charge. This is a representation of the electric field of a point charge. Last time we defined the flux, electric flux in this case, as the integral of E dot dA. So let's say we have a positive charge and we have a closed surface, and we need to know the total flux through the closed surface. So for that we need the area vectors, as we said before. So in order to calculate the flux through the surface, we need to have the area vectors. In the case of this surface that is perpendicular to the screen, the area vectors are to the right, and the electric field depends on the charge. In this case, this is a point charge, so the electric field is radial, and the electric field have different directions in different points and different magnitudes. So in order to calculate the electric flux will be a little bit complicated with this integral, but still that's the flux through the surface. And why it's gonna be complicated? Because in this case the electric field direction changes and also the magnitude changes. What we know now is that in this part of the surface the electric flux is a positive quantity because the electric field and the area vector are in the same direction, and in this part of the surface is also positive because the angle is less than 90. Now if we talk about the flux through a closed surface, I mean the total surface that is a box. This is a box. So in that case we call the total electric flux in a closed surface. The difference between the last equation and this equation is that you have a little circle in the center, and this circle in the center means that the surface is closed. That is, a box or a spherical surface is closed surface. So we have to integrate in the total surface the E dot dA. Now we know that in this case the total flux is positive because the electric field always makes an angle that is less than 90 degrees between the electric field and the area vector in any surface. It could be in that surface the same thing happen. The angle between the electric field and the area vector is less than 90 degrees, so the total flux should be a positive quantity. But now what about if we change the positive charge with a negative charge? You see, the electric field changes direction, so in this case will be to left, in this case will be directed to the charge, and you see the angles between the area vector and the electric field will be greater than 90, so in this case the flux should be negative. And if we add all these flux through all the surfaces, in every part of the surface the flux will be negative, so that means the total flux to the surface is negative. Now to calculate the flux is a quite difficult task, as we said before, because the electric field changes direction and changes magnitude. So we have Gauss' law. We have Gauss' law tells you that for a closed surface the total electric flux through this surface is equal to the charge inside, enclosed, inside over epsilon naught. That is sum of the charges inside over epsilon naught. So that's a very powerful law because it's telling you that this integral that is complicated to calculate is equal to the charge enclosed. You just have to add all the charges inside divided by epsilon naught. So it is a very interesting law. So if we have the same case as before, this is a positive charge and we wanted to calculate the flux through this box. We knew it was a positive quantity, but in this case it's not just positive quantity. We know the value, the electric flux, the total electric flux in a closed surface should be equal to the charge enclosed. In this case there is one charge, positive Q over epsilon naught. This is the value of the total flux. If we have a negative charge instead of a positive charge, it's just negative Q over epsilon naught. That's the total flux. So there are two ways to calculate the flux, the electric flux. If you have an open surface, then you have one option. The electric flux is the integral of E dot dA. So there is no option, because in this case it's an open surface. When you have a closed surface, you can use this equation, but also you can use Gauss's law. So the total flux through a closed surface equal to charge enclosed over epsilon naught is just for closed surface. For an open surface, you have to use the definition of flux. Now, in a closed surface, the total flux does not depend on the charge position, you see, because the total flux is just the charge inside divided by epsilon naught. So it doesn't matter whether the charge is there or the charge is there. The total flux will be the same. Now, it doesn't depend on the shape of the surface. So in this case, a spherical surface, the flux should be Q over epsilon naught. And in this case, it's Q over epsilon naught. It doesn't matter the shape of the surface. In a closed surface, the total flux does not depend on whether there are charges outside. So there is something wrong with this, but doesn't matter. So the point is that the electric flux does not depend whether there are charges outside or not. So in this case, the total flux through the spherical surface is Qi over epsilon naught. But if you have this case in which you have another charge that is external, it really doesn't matter. The total flux of electric field through this surface will be just the charge enclosed over epsilon naught. Interesting, very interesting law. Now, however, the electric field does depend on the position of the charge, the shape of the surface, and whether or not there are charges outside. This is very important, because we are talking about the electric flux. Gauss's law tells you about the electric flux. It doesn't tell you anything about the electric field. So for instance, in this case, the charge is at the center. The electric field should be, a very well known electric field in the position of the surface. Now, the electric field does depend on the charge position. Why? Because if you change the position of the charge, the electric field on the points of the surface should be completely different, but not the electric flux. You see, the electric field should be different, but not the electric flux. Now, does depend on the shape of the surface. So if you have a spherical surface, the electric field at the position of the surface should be very different from the electric field at the position of a cubic box. So the electric field depends on the shape of the surface, but the flux does not. Now, the electric field does depend on whether or not there are charges outside. So in this case, there is one charge inside. The electric field is, you can calculate the electric field at any point on the surface. But if you place a charge here, you change the electric field at any point because of the superposition principle. So at every point on the surface, the electric field should be different from before. So from this case, and this case will have different electric fields at the position of the surface. However, the electric flux is the same. The electric flux here is just the charge enclosed over epsilon naught, and the electric flux here is charge enclosed over epsilon naught. So that's why it's very powerful law. Okay, with this we finish.